doing it.
Welcome to Hashing It Out, a podcast where we talk to the tech innovators behind blockchain infrastructure and decentralized networks. We dive into the weeds to get at why and how people build this technology and the problems they face along the way. Come listen and learn from the best in the business so you can join their ranks.
That's an old school one. That's old. That was Colin's music. Colin made that music.
Oh, I didn't know that. I was like, this is corny as fuck.
That was the initial intro that we had.
Interesting.
I thought that was the video drop that D recently made. We could use that.
No.
Whatever. It's working. All right. Everyone who's watching, no one right now, maybe somebody later. We are on episode 3 of our ZKDL Camp, where we will go through the zero knowledge from, what is it, Distributed Labs?
Yep.
Basically, a bunch of lecture notes on learning zero knowledge. And we are going through still some math primers. We're going to start today with prime numbers and get through Chinese remainder theorem, I believe.
Yep. Through Euler's.
We'll get to the Euler's theorem.
Yeah. We're not going to go over Chinese remainder theorem. That's after Euler's. I read ahead a little bit.
No, Euler's is first, and then Chinese. Oh, sorry, Chinese and then Euler's.
Really?
In the book. The book is Chinese and then Euler's.
Oh yeah, you're right. Okay, never mind.
Right.
Yeah.
Last time we went through. What did we finish off of last time?
We were at primes.
No, what do we finish with? Euclidean algorithm. Extended Euclidean.
Algorithm. Extended Euclidean. Yeah.
So go check that out. A little more math prime. We're getting into a couple things that I guess will prove useful later on down the line when we get into ZK stuff. We're still doing math primers so that when we learn ZK stuff, it's not going to be worthless to us all. All right.
Mm-hmm.
You want to go ahead and start reading?
Sure. So yeah, 3 point. I did read a little bit, but there's some notation that I wasn't unfamiliar with, and hopefully we'll be able to tackle it together. And between us, Google, and ChatGPT or whatever we need to use. All right, so here we go. 3.3 prime numbers. Prime numbers are fundamental in mathematics due to their role of the building blocks of all natural numbers. In fact, every integer n greater than 1 can be uniquely factored into the product of primes, a concept known as the fundamental theorem of arithmetic, which we introduce in the next section. This property makes primes central to number theory and cryptography in particular, where we will use them in finite fields extensively. So that's like super important.
Yeah, that's probably like the main thing of like it's interesting. You can build any number from a factorization of primes.
Mm-hmm.
I think there's a really good Veritasium video on this.
There is.
Yeah, I think so. It's nuts. Go ahead.
Okay, so definition 3.16. Number p exists within the natural set of numbers n is called prime if and only if it is two. It's only two positive divisors are 1 and n. Definition 3.17. Number n that exists within the natural set of numbers n is composite if and only if there exists an integer a that exists within the natural set of numbers n, which is not 1 or n, for which a is a divisor of n. In other words, it is not prime. Example 3.8. For example, 3, 17, 19, 29, 71, 997, 7,817, and 104,729 are all examples of prime numbers. In contrast, 8, 1,001, 10,000, 100,000 are all examples of composite numbers. One might ask, what to do with the number 1? We consider it to be neither prime nor composite. Another logical question is whether the set of prime numbers is finite or infinite. The next theorem settles this question. Theorem 3.18, Euclidean theorem. If P is a subset of the natural set of numbers n is a finite set, consisting of prime numbers, then there exists a prime number p prime such that p prime it does not exist within the set P. Proof idea. So they're kind of doing a proof if you extended. They're basically trying to prove to you that there's an infinite amount of prime numbers.
Okay.
So theorem is like proof idea. We can set P prime, and then this is where the notation gets a little bit wonky and unreadable for me. How would you read that? Colon equals.
Is set to?
Okay, is set to, and then
Defined as?
what is
You
defined
set,
as?
Yeah, we can
What
set
is
P
the
prime defined as the
product of?
Product of, yeah.
The product of, and then like
What is that? What is that? I don't know what the big pi is. It's the multiplication version of a sigma, which is the summation.
Right.
Or the product of, I guess.
That's why like it's a product. It's a product of a series, and then in that series, it's like P exists within the P is like lowercase p is a number that exists within the set P, capital P, for P plus 1. So it's basically saying if you multiply the sequence of products of P plus 1 as you increment P within the set of capital P, then wait, what is the colon equals again?
Set to defined as
Is defined as? Okay.
That's what I usually do. I'll look it up. I'm looking it up now with haiku.
So it says, although it is intuitively clear that P prime is not divisible by any prime number in P, the formal proof requires a bit more effort. So yeah, that equation is a little bit not readable to me. I had to use ChatGPT earlier.
It's just product notation. Call the product. So instead of summation.
Yeah, but how would you read that? Like the subscript, like so it's the product of, and then
Product of
little
P within this exists within capital P of P plus 1, but the colon equals.
If you were to expand that series, that product of like series, like products of series,
yeah.
How do you get where it says, although it is intuitively clear that P prime is not divisible by any prime number in P, in capital P?
So let's see.
Like it's not intuitively clear to me.
P of P exists in P plus 1. So we'll just like
you just be like do P sub 1 plus 1, P sub 2
P
plus 1 to Pn, or to P sub n, like dot P sub n plus 1.
Yeah. Where
n is, I guess,
something, whatever the definition of the set is, right? So whatever
right, exactly.
P is some set, a finite set.
So how do you get that P prime is not divisible by any prime number in P?
So P prime is equal to this. Formal proof. It's intuitive clear. I mean, so P is a set of prime numbers. Okay. So prime number plus 1 multiplied together. I guess because all the prime numbers are in addition, they're plus 1, they're not going to be divisible by themselves. You multiply them together. I think from a previous than what we had last time.
Mm-hmm. No, I don't remember.
None of them,
what we had last
because
time.
they're all plus 1 from each other.
Then
none of them are going to be a divisor of the product of whatever P prime is. But I don't know why. P prime is also prime.
Like if it was a single P plus 1, like P prime is equal to, like it wasn't a product of the series of P plus 1, like p sub n.
Oh no! This is wrong. This is wrong. So like if we
What's
do this,
wrong?
this is wrong. It's actually
Oh, okay.
p plus 1. So it's all the primes multiplied together. The set of primes multiplied together plus 1.
Oh.
I think.
Oh. Okay.
Not
So the parentheses.
plus
There's no
1,
like
so it's
invisible.
going to be. So this is like this. So p prime is equal to
That makes sense then, because
1,
there's always a plus 1
P2
constant. You
plus
can't. It's not divisible.
3 pn plus
Yeah, that
1.
makes more sense. That makes more sense.
But why is
That's
the plus
intuitive.
1? How do we know it's a prime? Why? What I don't understand is why. How do I know p prime is a prime? I can see that it's not divisible because you add the plus 1.
Right.
I don't know why it's a prime.
I think they just defined it as a prime in definition 3.16. They just
I don't
said
think you can just
P.
define things as a prime.
No, they like this number p that exists within a natural set of numbers n is called
See what,
prime if
see
and
what
only if it
Plot
has two
say.
primes. Maybe they needed more information for us to make that.
Explain this proof idea. Let me take a picture. Easier for me.
ChatGPT did a good job explaining it, but I didn't spend time reading it.
See what Haiku has to say. I'll thinking. Let me switch my screen.
I'll
over
go ahead
to-
and read the corollary right after, and then once it finishes generating the
Oh, it's
response, then we can read it.
Let's
Oh, it's done?
switch over. Yeah. Blow it up a little bit. Beautiful proof of Euclid's theorem and the infinitude of primes. Here's the idea. Setup. Suppose capital P is a finite set containing all the primes. This is the assumption we're testing.
Uh-huh.
Okay. Is it just a finite set? Oh, it contains all of the primes. Okay.
Okay.
The construction. Define P prime as the product of all primes in P plus
Okay.
1. So I was right about it actually being all the primes plus
Parentheses.
1.
Yeah, they should use
Why P
parentheses. to make
prime
that-
reveals a problem. When you divide P prime by any prime P in the set of P, you get P prime is the, okay, plus 1 mod P. Okay. In plain English, the product of all primes is divisible by P, but adding 1 leaves a remainder. So P does not divide P prime. Okay, we got that.
Yeah.
This means P prime is not divisible by any prime in P. The conclusion. Oh, all primes.
Oh,
So it's by definition.
It's not
By
divisible
definition,
by-
it is a prime. It's not divisible by any of the primes.
yeah. Because then it would be composite.
Yep.
Okay.
Okay. Good job.
Thank you, ChatGPT.
ChatGPT.
Okay.
Fuck, I love AI. Okay. Window.
Corollary 3.19. There exists an infinite number of primes. Okay. Yep. Lemma 3.20. For all n that exists within capital N, set of natural numbers, capital N, where n, like little n, is composite, if there exists a minimal divisor d is greater than 1 of n, then d is a prime number. Consider a scenario where we have a large number and need to determine whether it is prime. How can this be achieved? In other words, what methods exist for primality testing? Several approaches are available. The most straightforward method is brute force division. Yep. Though it is impractical for large numbers. Yep. Probabilistic tests provide a more feasible alternative, though they introduce a small probability of error. In 2003, a significant breakthrough was made with the discovery of a deterministic primality test, which placed the problem within the P complexity class. It is also important to note that various types of prime numbers have applications in different fields. Examples include Mersenne primes, factorial primes, Euclidean primes, and Fibonacci primes, among others. As an example, consider one of the most well-known categories which you might encounter in the modern zero-knowledge protocols, Mersenne primes. Definition 3.21, Mersenne primes. The prime number of the form 2 to the p minus 1 is called a Mersenne prime. Am I saying that right? Mersenne?
I guess Mersenne.
Okay.
I don't know.
It looks French. It looks French. Okay. Where p is a prime number, usually notated as following: m sub p is equal to 2 to the p minus 1. Yeah. Example 3.9. For example, 2 to the 7 minus 1 is equal to 127 is a Mersenne prime, since 127 is a prime number. However, 2 to the 11 minus 1 is equal to 2047 is not a Mersenne prime.
Mersenne is how you pronounce it.
Okay. Since 2047 is equal to 23 times 89. As of 2025, only 52 such numbers were found, the largest of which is 2 to the really big number minus 1. I think that is 136,279,000.
Cartesian video, I think. Let's put that. I'm gonna look that up. I'll
Okay.
put it in the show notes.
Okay, so the exponent, for those who actually care, is 136,279,841. So 2 to that number minus 1. That's the largest found prime number. The Mersenne prime. Lemma 3.22. If the number m sub p is prime, then so is p. Mersenne primes are important in both number theory and cryptography. They have unique mathematical properties that make them useful for testing primality and generating large prime numbers. Yep. Mersenne primes are also crucial in the construction of efficient algorithms for error correction in coding theory and for generating random numbers in cryptographic applications, etc. Finally, we introduce the Dirichlet's theorem. This is probably like Dirichlet. Yeah, I was about to say it's probably a lay. Dirichlet's theorem, which is sometimes used for prime generation in cryptographic systems or constructing special primes. Theorem 3.23, Dirichlet's theorem. For any a, b that exists within the natural set of numbers n, if GCD of a and b is equal to 1, then infinite primes. Oh, then infinite. Oh, yeah, I put a typo here. Then infinite primes, prime numbers in the form of a, m plus b exists, where m exists within the natural set of numbers n. So, yeah, there's a typo there. I need to submit a PR. In other words, every infinite arithmetic progression whose first term and difference are positive integers contains an infinite number of primes.
Infinite arithmetic progression whose first term and difference are positive integers contains an infinite number of primes. AM, what is, okay. So that's a linear function.
Remember the generators, like when you have like
I'm just thinking about it off the top of my head.
Yeah. I think if you expand those generators, well, they're all based on Mersenne primes, right?
I don't know why that would be based on Mersenne primes.
It's just a prime number. Because it has to be. Yeah, we'll get there, I guess.
Explain Dirichlet's theorem. It's
nice.
Arithmetic progressions is a major result in number theory that generalizes what we know about primes.
Share it so I can see the math expressions.
Here, I'm gonna just go ahead and change what I'm sharing over to this, okay. And then we can use yours for reading.
Okay.
So to go back and forth.
All right, sir.
All right. We got so it generalizes what we know about primes. The statement: if you have an arithmetic progression, a plus d, a plus 2d, a plus 3d, which is what we have here with the am plus b. It's just backwards.
Yeah.
Where a is the first term and d is the common difference, and if greatest common denominator of a and d are 1, meaning that a and d share no common factors, then this progression contains infinitely many primes. what this means. Think of any arithmetic progression as regularly spaced sequences, 1, 4, 7, 10, 13. So, this is useful for mod, like for prime fields, right? I can see this being useful for prime fields. Because effectively, like, prime fields are just arithmetic progressions. Dirichlet proved that if the starting point and step sizes are coprime, you'll find infinitely many primes hidden in that sequence. Why it's powerful. It shows primes aren't just scattered randomly. They're distributed across all valid arithmetic progressions. You don't need a special starting point or spacing. They're everywhere. That's interesting. Examples. Primes of the form 4k plus 1. Infinite many. Okay, fine, whatever. Historical significance. This theorem, 1837, Jesus, was groundbreaking because it introduced analytic methods to number theory using calculus and complex analysis to prove discrete results about integers. It's a bridge between analysis and arithmetic. Cool. So it gives us tools to do analysis and rearrange things. And I think my intuition says is when we're looking at circuits again, gives us tools to restructure them such that they're more efficient.
Okay.
Let's look. What tools does this give us for a zero knowledge? I'm very curious my intuition is right.
Why do you use haiku? Is that
It's just faster. When I'm doing simple, smaller things, it's just
okay?
cheaper. It allows me to spend more. That's a sharp question. Thanks, Claude. Let's see. Many ZK systems need primes with specific algebraic properties.
Specific Sophie Germain prime
Guarantees
forms.
these primes exist in sufficient density. You can find them efficiently for cryptographic setup. Density guarantees relies on sampling from a particular residue. Tells you the primes need the
security arguments
aren't sparse. They're infinitely dense. That's nice. Group construction. Some ZK systems use groups built from primes and specific arithmetic progressions.
You know what this is related to? Like this is related to understanding the security factor that was disclosed for Fry-based proof systems in the context of what's the guy?
Oh, that one we talked about.
Benjamin.
Yeah.
What's his name? Starkware's thing.
Yeah.
Because I think it was a density guarantees issue because well,
look at this. But honestly, I'm not aware of a direct application of Dirichlet's theorem. Wonder how the book goes into it.
Apparently it starts at like chapter 11 or something like that. Like all of this is primer up until like, I don't know, like 200 something.
Maybe doing a lot of primer.
Yeah.
Whatever. Cool.
Yeah, it's fun to chat GPT, like seeing if your intuitions are correct or like seeing if there's any connection between
what these theorems are. I can just switch tabs. It's way easier.
Okay. I was gonna have to share my screen. All right. Or add to scene.
I'll read it.
3.4. Okay, go for it.
The fundamental theorem of arithmetic states that every integer greater than 1 can be uniquely factored into primes, which is fucking fascinating, which is crucial for understanding the structure of numbers. It plays a key role in areas like number theory, cryptography, and simplifying calculations involving divisibility. So, example 3.10, to see this fact in action, let us decompose an integer n, 1, 2, 3, 4, 5, 6, into a product of prime numbers. So 1, 2, 3, 4, 5, 6 is equal to 2 to the 6 times 3 to the 1 times 643 to 1. Obviously. Before formulating the fundamental theorem of arithmetic, let us consider the auxiliary lemma 3.24. Euclidean. If P is a prime and P is a divisor of A times B, then P is a divisor of A or P a divisor of B. Okay. An exercise as an exercise and to show where Bezier coefficients are used, let us prove both this lemma and the subsequent theorem. Proof. Let P be a divisor of A and B, A times B, but P not a divisor of A. Then the greatest common denominator of A and P is 1 because there are no common divisors. Okay, that makes sense. In which case, by Bezier identity definition 3.14, which we went to last episode, go watch that, there exists such a U and V that exists within the integers that A times U plus P times V is equal to 1. Let's multiply the left and right sides by B. ABU plus PVB equals B. Right? But P is a divisor of A and B, and P is a divisor of P and B. Makes sense. Therefore, their sum is also divisor by P being a divisor of ABU. Okay, let's see here. Okay. Make sense to you?
Not the sum. The sum is also divisible by P as a divisor of A times B times U plus P times B times V. Their sum is also divisible by that. Let's see. Is it 1 if you just divide them? If you take P as a divisor of A times B times U plus P times B times V and take the previous expression, like it should just be 1, right?
Yeah, I think so. P is a divisor of P and B. P is a divisor of A and B. Their sum is also divisor by... Oh, because of this AU plus PV, it was equal to 1. Maybe I don't get it.
So they multiplied the whole expression by B, right? So they had this previous expression on the second sentence, in which case by Bezier identity definition 3.4, there exists such U and V that exists with the natural set of, or the integer set of numbers Z, that AU plus PV is equal to 1. So that's the expression, AU plus PV equals 1. Then they just multiply into that expression this B, and they get ABU plus PBV is equal to B. And it says, but P is a divisor of AB. So P is a divisor of AB.
I can't see my screen anymore. I was going to bring up my thing. Write it down.
Okay, but that's what they said let. So P is a divisor of AB, and P is a divisor of PB. P is a divisor of PB.
Window.
Where did they get that one? Bezier identity 3.14. I think this is one that makes more sense to work out.
Yeah, I'm putting up the Miro.
Yeah. So the lemma 3.14, which is, I think was a, Bezier identity for any two given integers, A, B exists with a natural set of numbers n, with D is the GCD of A and B. There exists such a UV. Okay, that's not how. That's just the Bezier identity. That's something we've already accepted. So let me go back to here. Okay. So P is a divisor of PB. I'm not seeing that one. P is a divisor of PB. Oh wait, no, that makes sense because it's fucking PB. Therefore, their sum is also divisible by. Their sum is divisible by P. Okay, that jump, I need to work that jump out. P is divisors of ABU plus PBB.
So P
AB
is a divisor of A and B.
Oh no, I get it. It's because U and V are part of the part of the Bezier identity format. Okay. So the first term ABU is divisible by P because that's part of the setup. They said let P.
So it's showing
be
us
a
that P is a
divisor.
divisor of B.
P is a divisor of AB. The jump is P is a divisor. That's not even a jump. P is a divisor of PB. The jump is the sum of the two is divisible by P. And you can only make that conclusion based on the definition 3.14, that there exists such a UV, and essentially they're multipliers, such that P is a divisor of AB and BV. Or sorry, AB and PB.
Because of
Working it
the
out.
Bezier identity,
Because of the Bezier identity 3.14.
which are primes.
U and V, are they primes or are they just
They
integers?
exist within the prime numbers by definition. Here.
No, they're just integers. U and V.
Oh, yeah.
Or-
Z is integers. I forget. Sorry.
Yeah.
My bad.
Yeah, U and V are not guaranteed to be primes. They're just integers. In fact, they're always positive, right? Because the Bezier identity in the context of this type of cryptography, you don't like it can be positive or it could be negative for both U and V, but it says you make the assumption
Did that
it's
code.
always positive. Yeah.
Okay.
And it's a big number. I feel like a lot of these would be more helpful to just code out and then also handwrite. Like handwrite, then code out.
I'll try coding out, I guess. Theorem.
Yep.
Can't see that on the upside down or the
No.
mobile
Now we
stream.
are ready
Whoever's
to
watching this
introduce-
mobily, we're sorry. Go to a computer. Theorem 3.25, fundamental theorem of arithmetic. Any integer n greater than 1 can be decomposed in the unique way into a product of prime numbers. So n equals a piece of 1 to the alpha 1, piece of 2 to the alpha 2, all the way to pt, the alpha t. So product from j to 1 to t, piece of j, exponentiated by a sub j, where piece of 1 to p2 are prime numbers, and the set of alphas exist within the natural numbers.
Oh, interesting.
Okay.
They're not even guaranteed to be they don't have to be integers. They can
Mm-mm.
just be natural numbers. Okay.
That makes sense. Really? Interesting. Yeah. Proof. We need to
Oh no, it
prove
says
both
any
existence and
integer
uniqueness.
n.
Exponentiation is integers.
Yeah. So you
Natural numbers is
So is that a
it can
typo?
be
So
negative. It can be negative.
the last no, but the last line says alpha 1 to alpha. So alpha 1 to alpha t exists within the natural set of numbers n, but in the beginning, in the second sentence, or I guess it's the first, any integer n is greater than 1. Now,
And
if
natural,
you're
they're counting numbers. So they can be negative.
No, but what I'm saying is that it should be swapped out from natural numbers to z, because right? Shouldn't it be the integer set z?
No, because they can be negative.
Yeah, but it doesn't need to be like
Natural
integers
numbers
can be negative.
Natural
You
integers.
see my point?
The integer set z, I believe, is
Integer set is a
positive.
subset of natural numbers, but they gave you a statement saying any integer n is greater than 1. That means that the set, like, yes, the set can be natural numbers, but it would probably be more accurate to say z. No.
I'm asking.
Okay.
Z is the integers, which can be negative. Oh, natural numbers are not negative. Okay, so they can't be negative. Z is the integers, which can be negative, including 0. Double strike in is the natural numbers, which starts at 0 and goes forward. I guess there's a convention where sometimes it doesn't actually start at 0. Interesting. Anyway, so in the natural numbers is a subset of the integers, because the integers can be negative.
Okay.
So there you go.
Oh yeah. Never mind. I'm wrong. for whatever
smart
reason, the was it the integer over natural? Yeah, rational. Okay. I just need to refer back to the notation notes that I have here.
Okay. Cool.
Yeah, that makes sense. Okay, proof.
We need to prove both existence and uniqueness. Since the existence is easy to prove, let us make the small exception and show it. For other proofs, I don't think that's how you say that.
Yeah.
In
The
particular, for the uniqueness case, that's that for other proofs.
Yeah, it's proofs.
See the literature provided. Okay, existence. Suppose the theorem statement is false and there exists an n that does not have such a representation. Let n sub 0 be the smallest of them. If n sub 0 is prime, it can be represented as p1 equal to n sub 0, a1 equals 1, which satisfies the representation. Therefore, n sub 0 must be composite, which means, what is that, for all a, right?
Yeah. Yep.
For all a and b that exist within the natural numbers, 1 minus a, b minus n sub 0, such that n is equal to a times b. Since n sub 0 is the smallest non-decomposable number and a, b is less than n0, a, b can be represented as a, basically the fundamental theorem of arithmetic there.
There exists. Sorry, you said for all. I was wrong.
Okay, there exists. Okay,
there exists. Yeah.
E for exists. Don't forget that.
It's I think upside down A is for all.
Yeah, that's right. Thank you.
Yeah.
Therefore, basically, you're expanding A and B via the fundamental theorem of arithmetic we just showed. Okay. Therefore, n sub 0 is equal to A times B is equal to the product of both of these things. Thus, the contradiction as n sub 0 is represented the product of primes.
I didn't understand that.
Trying to see what the negative is because you're trying to prove the opposite of the existence. So like saying like we'll try and say there's a negative. We're trying to say there exists one that doesn't satisfy this, and then expanding them out, you show that it's a bad statement.
Got it. Suppose the theorem is statement is false and there exists n that does not have to be, or that does not have such a representation. Let n sub 0 be the smallest of them. If n sub 0 is prime, it can be represented as p sub 1 is equal to n sub 0. Alpha sub 1 is equal to 1, which satisfies the representation. Therefore, n sub 0 must be composite, which means there exists ab exists with a natural set of numbers n. 1 is less than a, b is less than n sub 0, such that n is equal to ab. Since n sub 0 is the smallest non-decomposable number, and ab is less than n sub 0, then a and b can be represented as a is equal to p sub 1 to alpha 1. So it's a product expansion of a and b. Therefore, n sub 0 is equal to ab is equal to the.
Is that because basically that expansion is the same as the actual theorem, which then just becomes the exact same representation?
Maybe let me look. Thus, the contradiction as
if it's a composite, then you get this representation, which actually just being the original representation of the fundamental theorem of arithmetic, which is a contradiction, right?
Yeah,
it's still just a product of primes. So
they're always saying it always comes down to being a product of primes.
It's so what you're saying is by making it a composite and expanding those things as the fundamental theorem of arithmetic, you end up with the same thing, which is just a number. So you're saying the representation still holds.
Yeah,
there is no way to show that there doesn't exist a number that can't be expanded this way, because when you theoretically make one, and it still shows to be expanded that way.
Yeah, I get that that's the argument, but it's just not intuitively clicking for me, I suppose. N sub 0 be the smallest of them. N sub 0 is prime.
Because like this one here, if
N sub
it is a
0
prime, then it already satisfies the representation. So it's cool. That's not going to work. So that means like, okay, let's look at what it means to be a composite number. A composite number means that there's A and B, right?
Yeah.
And since you can define both of these things as
a product of primes,
them as a product of primes, when you
satisfies the
add
fundamental
them to me,
theorem.
this is still a product of primes, which is the original statement, which is the representation. So like, there is no situation in which you can't have that representation.
Yeah, no, I get the argument. It's just I always have issues with proofs of statements because it always like they use the statement to prove the statement, and it's just like wonky for me. It's like what? It's like
it's got electrolytes. It's what plants crave.
Yeah, that's what it logically sounds like to me. It's like
because it's got electrolytes. What is electrolytes? Because that's what plants crave.
Yeah, exactly. It feels circular in logic, but okay.
Whatever book. Suppose N is decomposed as, and I'm going to run out of time here. Definition 3.25. Then if D is a divisor of N, then D is equal to representation. Where, got it. Suppose A is that representation and B is that representation, then the greatest common denominator can be evaluated as the greatest common denominator, which is the product,
which is the product of
the minimum.
Minimum product of primes. Minimum.
P exponentiated to the minimum of alpha I or B of I. Well, that's interesting.
What does that evaluate to? The minimum of alpha sub I and beta sub I. Like, what does that evaluate to?
So you take all of the alphas and all the betas,
and you just take the smallest one, and then you exponentiate P to that.
The smallest of the. You can do this basically based on the way exponents work. When you multiply two numbers that are exponentiated together, you add, and so this ends up becoming. I think that's how you would prove it. Lowest denominator is the max of. That's interesting. Okay,
so it's opposite. The GCD is min. Yeah, I guess it makes sense. LCM is max.
If B is divisor of A, C is divisor of A, then greatest common denominator of B and C is equal to 1.
I feel like I'm missing more extensive proofs on all of these statements. Does that make sense? Like, there's
throw them all in ChatGPT and have it walk you through each one, and then be like, that doesn't make sense. Expand more.
Yeah.
Or I explore for these things. I mean, Haiku seems to be doing a pretty good job here.
I'll try that after.
We could write them all. We can ask all your questions, then copy and paste the answers and put them in some show notes.
Yeah, that'd be a good idea.
Implications and applications of the fundamental theorem of arithmetic are large and important, and the number of obvious ones are listed above. Okay, obvious, quote unquote, obvious. Remark: note that the problem of factorization, in other words, finding the decomposition of a number into prime factors, is in the NP class of complexity and is the basis of certain crypto systems such as RSA. Yeah, cool.
They should have had like a primer on complexity theory,
I love complexity theory.
It's like whole books on that shit.
People spend their entire lives on complexity theory, but like, yeah, that's a fun place for your brain to explore.
Yeah.
All right, you want to do modular arithmetic? We'll do a little more.
Sure. 3.5 modular arithmetic. Now we are ready for practical applications of number theory, starting with modulo congruence. In this section, we will review the idea of congruence, learn how to use it, and explore its key properties. Understanding these properties will help simplify calculations and solve problems more efficiently in fields such as cryptography, algorithms, and number theory. Definition 3.27. Two integers a, b exist within the integer set z are said to be congruent modulo n exists within the natural set of numbers n, if and only if n is a divisor of a minus b. We denote this as a. We denote this by a. Is congruent to b mod n?
I guess that means congruent. What is the?
I think triple bar is congruent. See,
with another bar.
Oh, wait.
Congruent symbol.
Yeah. Okay. So I guess I
Really
read that
use the
A is
modular
congruent.
arithmetic to mean is congruent to. So
So A is congruent to B mod n.
B mod n.
Yeah. Okay. All right. Example 3.11. It easy. Okay. So I'll just make another.
Okay, so that meaning, here goes, the meaning of A is congruent to B mod n is equal to saying A and B leave the same remainder when divided by n.
Okay. Should write that out. A and B leave or divided by n.
A, meaning A and B leave the same remainder when divided by n. So congruence. So like, let's say, as an example, I may have an example here. There we go. They give an example right here.
Yeah, so I put A and B divided by n have the same remainder. I just worded it another way.
Yeah. If you write it all out, you get the same remainder. So 17 is congruent to 5 mod 12 because both 17 and 5 leave remainder 5 when divided by 12. Three is congruent to 8 mod 5 because both leave remainder 3 when divided by 5. Does that make sense?
Interesting. Yep.
Okay.
Example 3.11. It's easy to see that 26 is congruent to 5 mod 7 since 7 is a divisor of 26 minus 5. As always, we enumerate some key properties of congruence modulo n relation to better understand its nature. First, we consider the properties of reflexivity, symmetry, and transitivity to confirm that congruence modulo n is what is called an equivalence relation. For general equivalence relation definition, see section 9.3. Lemma 3.28, reflexivity, symmetry, and transitivity. 1, A is congruent to A mod n. 2, if A is congruent to B mod n, then B is congruent to A mod n. 3, if A is congruent to B mod n, then B is congruent to C mod n, then A is congruent to C mod n.
You ever seen the clock visualization for modular arithmetic?
I feel like I have a long time ago. You want to pull it up? Because it goes to 12 and then you just mod numbers on the clock and it just...
Yeah, so like, yeah. So we'll say mod 12. That's what's easier for people to understand.
Yeah, the clock is mod 12, right?
Yeah.
Inherently. Yeah.
So if you had like 13,
then it's 1
mod.
It's mod 12.
Mod 12.
That's 1
equal to 1 because like 13 goes around the clock
once and then overlaps
leaves
until
1 over, right?
Yeah.
So like whenever you have mod 12, it's just going around the clock over and over again.
Yep.
Until you subtract whatever this number is. You just keep doing it over and over again until. So if you it's like what.
So like anything that's less than 12, not less than or equal to 12, but less than 12 would just be that number. Because if it's 1, yeah, exactly.
Mod 12
it would be 4.
2 revolutions of the clock, which would be 24.
Right. 2. Right. Or 2, yeah.
Right. So 1 revolution of the clock would be minus 12. So that would be 14. Do it again, minus 12. Okay.
Yep. You just do divide by 12 and then the remainder is your modulus.
Yeah. That's always been kind of a nice, like my intuitive visualization of modular arithmetic.
Yeah.
I don't know if it helps anybody else that's watching, but it helps with like you're pulling out each time. But like it's like you end up, if you were to like count the clock, right? You end up with 2. So you end up like the clock out for 26 modular 12, you end up here. Okay, so your remainder is 2. Right? Because you're going around the circle. You have 2 left over, 1, 2, cool, your remainder is 2. You just keep ticking it like that. I don't know. Useful for me, kind of.
Yeah. I think Khan Academy has some other ways to visualize non-mod 12 base numbers systems, but
that's the same thing. It's just like it's not a clock. It's just a circle of numbers.
Yeah, exactly. Oh, wait. There's aren't there other visualizations other than a clock or no?
I mean, it's secular, I can't say the word.
Circular?
Cyclic system. It's a cyclic system, meaning that it goes over. It's going around. So I mean, even this. So like 1, 2, 3, 1, 2, 3, 1, 2, 3 is a cyclic system because this is modulo 3. It just repeats itself. So you could represent that as 1, 2, 3, and then going around in a circle, right? Doing like that.
Yeah.
You just keep doing it. So it's just a different linear representation of mod 3 versus just putting them in a circle and going around a clock. Quote unquote clock.
Yeah.
Speedometer is usually a good way to put like once it's over, it starts over.
Mm-hmm.
It's just whatever the mod is the number of times you count before it starts over.
With the speedometer or the accelerometer? Or is
Odometer.
it neither? Odometer. Oh yeah. Because you can just reset it.
Yeah, once it's on the 9.
You just manually. Oh yeah. I've never maxed out an odometer before.
Oh, I don't know if anyone has.
Like,
that's a lot of miles, and we don't make cars like that. All right.
Interesting.
Let's see what else. How much do we got left here? We got quite a bit.
Yeah. Where did we leave off?
Let's leave it at that. We left at 25 for round number.
Sounds good. I read the lemma 3.28. I didn't read lemma 3.29. Let me just read the last two. Let me read through 25. Yeah. So after reading the lemma 3.28 on reflexivity, symmetry, and transitivity, in turn, the following lemma states that we can perform addition, subtraction, and multiplication on the congruent numbers modulo n. Similarly to the usual arithmetic, lemma 3.29, suppose we have A is congruent to B mod n and C is congruent to D mod n. Then 1, A plus or minus C is congruent to B plus or minus D mod n. 2, A times C is congruent to B times D mod n. Example 3.12, let's see how the lemma works in practice. 17 times 26 mod n is congruent to 3 times 5 is congruent to 15 is congruent to 1 mod 7. 5 times 26 mod 7 is congruent to 5 plus 5 is congruent to 10 is congruent to 3 mod 7. Negative 5 times 13 mod 7 is congruent to 7 minus 5 times 6. So 7 minus 5 is in parentheses times 6 is congruent to 2 times 6 is congruent to 12 is congruent to 5 mod 7. I need to work those out, and then I'll be like, yeah, okay, makes sense.
Yeah, working that out.
I can't just look at 26 mod 7 and just like know that.
Let's see.
Or 17 times 26 mod 7.
How is 3 times 5? So like 17 mod 7 is 3. 26 mod 7 is 5. Right? So 17 times 26 mod 7 is congruent to the remainders multiplied together.
Oh, okay. 15.
Right?
Got it.
Equals
3 times
15,
5.
which is equivalent to 1 mod 7. The 1 mod 7 doesn't quite.
Yeah, how did you get the 1 mod 7?
Where's the 1 mod 7 coming from? Oh,
you just take 15 itself.
15
it's essentially
15 is,
like mod 7. If you do 15 mod 7, you get 1.
Yeah, I see that.
So it's 1 mod 7. See, let me read the lemma again. Let me reread the lemma. Suppose we have A is congruent to B mod n. Wait, no, that's not the one. It's lemma 3.29.2. So AC is congruent to BD mod n. So, because it's 17 times 26, that matches the format BD mod n. So 15.
So the first part, 3 times 5, we got that right. And we have to go backwards back into mod. So that transition backwards in. All through mod 7.
They don't say that in the lemma, huh? B mod n? Oh, AC is 3 and 5. So
Yeah.
A.
Yeah, 3 and
So
5
then
is the first one. So 3 and 5 is A and C.
Yeah, so then if you put it in the format A is congruent to B mod n, no, that's
What is B mod n for 17?
yeah, I'm trying to find.
So let's see here.
I need to write this down.
17 times 26 mod 7. So 17 is, let's see. For 17, we have, what is that? A is equal to 3. And so seven goes into 17 twice. To 2. What is B in this scenario? Is that going to be 17? Yeah. Six. A is equal to 5. So we have 3, which is congruent to 17 mod 7, and 5, which is congruent to 26 mod 7. And so what is C here? So we were using the AC equal to BD mod N.
Yeah, so I have it in the format A is congruent to B mod n. I have 17 is congruent to 3 mod 7. And then for the format C is congruent to D mod n, I have 26 is congruent to 5 mod n. But like I like intuitively I can just look at the pattern, but like I'm trying to make the math.
3 times 5 is equal to 15. Where BD in this scenario? Oh, B is 17.
Is it?
Yeah.
Okay. So like you can put it in 3 different formats. You can put it in BD mod n is equal to AC. And if you do that, then it's 17 times 26 mod 7 is equal to 15, where A is 3 and C is 5, and B is 17, D is 26, like you're saying, and then N is 7. Well, you could do it all in the other format. A is congruent to B mod N, and 17 is congruent to 3 mod 7, and then C is congruent to D mod N, which is 26, is congruent to 5 mod 7.
Where's the 1?
I'm trying to simplify. Anyway,
Where's the 1 come from? Because that, I mean, like 15 mod 7 is 1. They are congruent to each other. I guess they're just all congruent to each other.
the whole like it, so 17 times 26 mod 7 is congruent to 1
It's
mod 7.
converting from like cyclic arithmetic to linear arithmetic. It allows you to convert. You can take 17 times 26 mod 7
Uh-huh.
and then just do the modular of each of the factors.
Yeah.
And then that's an easier
You get 3 and 5.
multiplication.
Right.
Gives you 15. And then just
Right.
convert back. You get 1 mod 7. It's congruent, I guess. So you in the end, you have 17 times 26.
So
is equal to 1.
I guess my
the remainder of 1726 mod 7 is 1 mod
the
7.
remainder of
Something like that.
yes. But like the lemma doesn't give you the simplification. You're doing the simplification in the example.
Yeah.
Like
take some playing with.
I think they're missing. They're like because in the first format, 17 times 26 mod 7 matches the format BD mod n, right? Which is AC. The second item in
second one's the
Unit
same, yeah.
3.29. And then it's taking that same lemma, AC equals BD mod n, but you're putting in the format 15 is equal to, like 15 is AC, is congruent to BD, which is now 1. So BD was previously 17 times 26, and then you convert it to 1. There must be, anyway, there must be like an addition. Oh, wait, what was this?
All right. I got to go.
All right. Sounds good. I'm going to do this outside of the...
If you're watching, tell us how you feel about that.
All right. How do we want to end this? That's it? Just hit end?
Goodbye. See you next week. Next week we'll go over
What's your sign off?
more of this. Goodbye. I don't know. I have a sign off.
All right.